the series. Ceres semi-major axis. The semi-major axis is half of the longest diameter of an ellipse, and the semi-minor axis is half the shortest diameter of an ellipse. This diagram, which you see on the left, shows Ceres' longest and shortest distances from the Sun, where mu is the longest distance and theta is the shortest distance. So as you can see on the diagram, the longest distance, which is represented by mu, the Greek symbol mu, or the Greek letter mu, is what we call the aphelion, and that is equal to 2.98 astronomical units for Ceres, for that planet, that dwarf planet Ceres, and which is also equal to 446 million kilometers. And then the theta is what we refer to as the perihelion, and that is equal to 2.55 astronomical units for Ceres, which is also equal to 381 gigameters. That GM is gigameters. So that is how we look at it. Then we go back to our note, which says, for the following worked examples, let us make Z the semi-major axis, which we refer to as the semi-diameter. So as you can see, our working will be Z, which is the semi-major axis, is equal to mu, which is the aphelion, plus theta, which is the perihelion, all that over 2. So it is basically the sum of the aphelion and the perihelion divided by 2, basically like we're finding the average. And then that would be basically equal to 2.98 plus 2.55. Just pardon us, they are not in more than 3 significant figures for accuracy, but we'll just deal with that. We will still get a better accurate or precise answer, divided by 2. So then our Z will be equal to 2.765 astronomical units. That's in the 4 significant figures, and that's approximately equal to 2.77 astronomical units, or basically it's equal to 414 million kilometers, or 414 gigameters. That's 3 significant figures for accuracy. So I want us to understand this phenomenon of the orbit and an ellipse before we look at the next item. So let's read what's on top there. Mars, Ceres, and Jupiter in orbit around the Sun. So they're in orbit around the Sun, respectively from the Sun. So basically, that red orbit, the orbit is that oval path, or that oval ring, not a ring rather, but like an oval path, where the celestial object, which is that planet, moves as it goes around the Sun, or as it orbits the Sun. Basically, that's what an orbit is. So we have the red orbit, and we have a planet that's there, that's Mars. And then the white orbit is the orbit for the dwarf planet Ceres, which we are looking at in this video. And then we have Jupiter, which is that final one, that large planet. I don't know what it's not to scale, but if you were to see it, it will be very large, larger than all these other two. It's in that brown orbit. So that's basically the idea. And that other object that's at the far right there, that's the Sun. Now let's look at Ceres orbital period. So that diagram which you see on the left, that's basically the same diagram which you saw just now, but now it's like overhead. It's like on top of the planets and the Sun. I hope you can just understand. We just had to remove the other orbits so that you can clearly see something, because it's not a perfect orbit. It's supposed to be like an oval shaped orbit, but just try to visualize the idea. We're trying to make you understand the phenomenon. So let's look at the note at the bottom corner there, the bottom left corner. According to Kepler's third law, which states the squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axis of their orbits. Therefore, Ceres orbital period is therefore. So by rearranging the equation of Kepler's law and making the period t the subject of the formula, we then get the formula that we can use, the alternative formula, which is easier to use with the variables that we already have. So that law is what we see, the Kepler's law is what we see presented in front of you, which is t squared over r cubed. If you read that law, you'll find that these two variables are proportional, and that will be basically equal to t squared over z cubed. We have taken z as our semi-major axis from the previous calculation, so you should be familiar with that. So what to do, or rather, the original formula is t squared over r cubed is equal to 4 pi squared over gm, where r is the separation of the masses, or separation of those orbits that we're talking about, but we are now using z because that's the one we used in our semi-major for our semi-major axis. So as we rearrange, we take that z cubed variable and then we take it to the right, the other side of the equal sign, and then we end up with t squared is equal to 4 pi squared times z cubed, or multiplied by z cubed, all over gm. Our g is the gravitational constant, and our m, the capital letter M there, that is the mass of the largest object of the two objects that we are analyzing, or rather we just call it the larger mass. So now we need to take the squared on the t to the other side, so that we remain with t as the subject of the formula. That's what we mean. So our t is equal to 4 pi squared, the square root of the 4 pi squared, multiplied by the square root of z cubed over gm. Therefore, our period t will be equal to 2 pi multiplied by the square root of z cubed over gm. And all of these variables on the right side of the equal sign, we have them, they are known. The only unknown is now the period which we are going to calculate just now. Substituting the variables with the actual quantities and converting the period to years. These years, they are not the light years that you usually hear in astronomy. These are earth years, so that we make it relative to our normal type of years, our time. So the period is equal to 2 pi multiplied by the square root of z cubed over gm, which is the equation that we derived, and that will be equal to 2 pi multiplied by the square root of 4.14 times 10 to the power 11. That's 414 million kilometers, and that will be cubed. That's our z cubed, and that will be over 6.674 times 10 to the power negative 11 multiplied by 1.99 times 10 to the power 30. That will be equal to 145,231,472.5 seconds. These are earth seconds relative to our time, and that will be the period in terms of seconds. But remember, we want hours to be in years so that it's easier to relate. These figures are too large, so I'm going to do the conversion step by step. So therefore 145,231,472.5 seconds into minutes, we'll have to divide that figure by 60 seconds, and that will give us around 2,420,524.542 minutes. And then we divide those minutes by 60 minutes, because we have 60 minutes in an hour, we have 60 seconds in a minute. That's the idea behind it. So we then get around 40,342 point blah 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 hours. So those hours, we divide them by 24 hours, and then we get those number of days, because we have 24 hours in one day. So our days will be equal to that, and that's approximately equal to 1,681 days. Basically, those are the number of days that it takes for CERES to orbit the sun, for those who are not yet understanding what's going on. So we then move on, then we get that value of days. We just don't use that whole number, we use the whole approximation with the decimal, so that we approximate the value, and we have an accurate calculation basically. So we divide that by 365 and a quarter days, because we have 365 and a quarter days in a year, not the leap year. We are not including the leap year here, we're just looking at the normal year. So we then get 4.6021 Earth years. So the orbital period will therefore be approximately equal to 4.60 Earth years, correct to 3 significant figures. Quite a long time. Now we move on to our last one for for this video, our last calculation. So we're looking at CERES average orbital velocity. So that's basically the speed that CERES takes as it moves in its orbit around the sun. So where g is the gravitational constant, we looked at that, and the capital letter M is the larger mass. In our case, it is the mass of the sun. For the mass of CERES, you'll find that even when you look at Newton's law of gravitation, you might look at the smaller m as well being included, and that smaller m will represent the mass of CERES. That's for extra information. You don't need that for now, but just so you know. And then and z is the proposed separation between CERES and the sun, and that we defined it as the semi-major axis. Let us find v bar, which is the average orbital velocity. Apologies for the spelling of axis. It's supposed to be A-X-E-S, exactly, not I. Okay, so as you see, our v bar is the v with that horizontal line on top. That's what we mean, v bar, and that is average velocity, will be equal to the square root of gm over z. Yeah, you can do the conversion and the rearrangement of the formula from the principal formulas, like the angular velocity and the law of gravitation and all those. Just do that convention by yourself. We try to explain to you how we get these formulas, these funny formulas. We just do some rearrangement and we get the subject of formula. So we just did it and we got this v bar, which is equal to gm over z, the square root of gm over z, and we've already defined those variables, and that will be equal to that 6.674 times 10 to the power negative 11 times 1.99 times 10 to the power 30 over 1.14 times 10 to the power 11. That's the million kilometers, that 11, and then that will be square rooted, and then we get 17,910.98494 meters per second. And then meters per second, that will be a very small unit, yet we have a very large figure, so we need to change that to kilometers per second. So since kilo means 1000, therefore we're going to divide that meters per second by 1000 meters, and then we're going to get 17.910 blah blah blah. We'll not look at all those other decimals. So basically we'll then say, therefore our v bar, which is average orbital velocity, will be equal to 17.9 kilometers per second, correct to 3 significant figures. And we have completed our calculations. It's just so that we appreciate where we get these figures. They don't just come from nowhere. This is how we get these figures. More on CERES. Narraunda ya CERES. Stay tuned for more. Siyabonga kakhulu.